Thank you so much. Thank you for being here. It's a real privilege to talk to all of you. I hope you had a good lunch. And okay, so let's start. What I'm going to talk to you about today is how to compress proofs using cryptography. Okay, so proofs. What are proofs? So, proofs usually are these long, horrifying things that you need kind of to verify. And it's a very, very painful thing to do for those of you who try to verify proofs. So, won't it be nice if it were possible to make proofs actually very short and easy to verify? So, what is our goal? I would like to take a very long and possibly complicated proof and convert it into a very short, easy to understand proof. Won't that be wonderful if we can do it? Okay, so that is my goal, yeah. However, it's impossible. Sorry, guys. Okay, but I'm not done, so stay with me here. The reason it's impossible is because sometimes statements can be very hard to know if they're correct or not. And if proofs were very short, you can just enumerate over all of them and see which one verifies and which one does not verify, and then determine if the statement is correct. So if the statement is very hard to determine if it's correct or not, we don't expect to have these succinct proofs. However, what I want to tell you about today is that cryptography, and actually I'm sure that many other disciplines around here, are kind of magical in the sense that when you think kind of in a straightforward way, often you hit impossibility results. You try to do something and you notice it's impossible. And in cryptography, that is almost always the case. You try to do something very fast, you realize it's impossible. And the way I think of cryptography is kind of as an art of overcoming these impossibility results. And what I want to talk about today is how to use kind of the magic of cryptography to make proofs succinct. Now notice, proofs have nothing to do with cryptography. Why is cryptography coming in here? What's the connection? I'm talking about proofs. Why am I talking about crypto here? So I'm going to tell you why. But before I do so, maybe some of you who don't necessarily write proofs or read proofs for a living may say, actually, we don't care. I don't care about proofs. It's not my life is not about proofs, so I don't care. So before you leave, let me tell you that you should care. And the reason why you should care is because, as we know, we're in the brisk of kind of a digital revolution. And today, a lot of the computations that we do are no longer done on our own trusted machine. Many of our computations are now done on untrusted platforms. It can be blockchain technology. Now, even to verify a single transaction, is a huge computational burden that often we do not do on our own machine. We just assume that we'll have a succinct proof or assume that the transaction is valid. And as we saw in the previous panel, with AI, kind of the new kid in the block, not so new anymore, that you ask questions, it gives you answers. How do we know that it gives you the correct answer? So because our computations now are outsourced to possibly untrusted platforms, we all need to have these succinct certificates or succinct proofs that certify correctness of answers. Okay? And these things are actually used now. Currently, it's primarily used in blockchain technology. Most notable is Ethereum, which is one of the biggest companies out there. They use these succinct proofs on their chain. So with that, hopefully I convinced you that it's an important problem to study. And now the question is, how do you use cryptography to break this impossibility barrier, is the question. Okay, so let me tell you how this is done and what's our goal. So we want to take a long and complicated proof, let's say W for witness, for some statement X, and convert this gigantic, long, hard-to-verify proof into this succinct certificate that certifies the validity of the long proof. So, what is the guarantee that we want from this certificate? We call it soundness guarantee. What is the guarantee we want? We want it to be the case that if the statement is false, if X is false, you should be able to generate a certificate. You can generate a certificate only for true languages, otherwise, what's the point? Okay, so this is kind of a must guarantee to have, but we can't have that guarantee. As I mentioned, there's an impossibility. How would we overcome this impossibility? So here's the idea that one way to overcome this impossibility, you know what? We don't necessarily say it's impossible. We're going to say practically it's impossible. Meaning, there may be fake proofs for false statements. Maybe, but it's really, really hard to find. More specifically, the guarantee we give is if there exists an adversary that manages to find a fake proof, a fake certificate for a false statement, then it means we can use this adversary to break some underlying cryptographic assumption. That's where crypto comes in. In other words, for example, we say if there exists an adversary that generates a succinct certificate, a valid certificate for a false claim, then we can use this adversary perhaps to factor large numbers, something we believe is impossible. That's just one example of a cryptographic assumption. We have a lot of kind of hardness assumptions that we assume in cryptography. Actually, almost all of cryptography is sound, is secure under some hardness assumption. And now our idea is, let's make proofs succinct by assuming some hardness assumption and that guaranteeing that, the only way a false proof someone can generate a false proof is by breaking our assumption. So if you believe that it's hard to factor large numbers or whatever assumption it is that we rely on, then you can relax and know that nobody will be able to find these succinct proofs because you believe that nobody can factor large numbers. Okay, so this is the definition. This is kind of the idea of how we get around the impossibility result. And we call this, instead of soundness, we call it computational soundness. Okay, because it's hard to find a proof, not a fake proof, not that it does not exist. And the jargon we use for this is succinct, non-interactive, argument. Argument is just kind of a more relaxed word for proof. We can't really say it's a proof, because a proof, there's never false, like a correct proof for a false statement. So a more relaxed version is we say it's an argument. It convinces us that the statement is true. And now you may wonder, why non-interactive? Proofs are always non-interactive. Why am I emphasizing this? You'll see in a minute. Okay, and kind of the jargon for this is snarg. Okay, so what I want to tell you for the rest of the talk is to tell you a little bit about our journey as a community and my personal journey of kind of coming up with these snargs. And let me start with the most important and the best part of this journey has been my collaborators. So my students on top, my postdocs, and my colleagues. They were kind of the best part of this journey. I think, in my opinion, the best part of every journey is the people who take the journey with us. I spent endless nights, hours, happy moments, sad moments, tears, sweat, everything with these people. So these journeys are never easy. There's a lot of ups and downs, and it works, it doesn't work. Happy moments, you're sure it works, and then like you fall because nothing works, and so on and so forth. So it's been really a fun kind of roller coaster for over 10 years that we've been doing. Okay, so with that, let me tell you where kind of this journey really started. And it started with this notion of zero-knowledge proofs introduced in the mid-'80s. So what is a zero-knowledge proof? A zero-knowledge proof is a proof that reveals no information about why the statement is true. Okay, so you read the proof, you verify it, but you get no information of why actually the statement is true. Now, typically we want the opposite of zero knowledge. Right? When we read proofs, we want to actually understand what is going on. And many of us tend to write proofs that are completely not understandable, and it's frowned upon. You want proofs that actually give you knowledge. Cryptographers are a bit weird, okay? We want proofs that give you no knowledge. And the reason we want it is because often what's the knowledge inside it corresponds to some secrets that we have and so on, and we want these secrets to remain hidden. So their goal was to construct proofs that give no information, no knowledge about why the theorem is true, why the statement is true. And guess what? The first thing they noticed is it's impossible. Any proof, any way you try to define what it means to know, defining this is non-trivial. But kind of any way that you think how you define that you get no information, seems like you can't get it. And the reason is because if you think of a proof, it's information. It's worth something. You can sell it. So no information. It has some information. You can verify it. And it's worth something. So you can't really say it's no information. Okay, as I said, crypto, you always hit these impossibility results. What do you do when you hit impossibility results? That's when the creativity starts. Then you need to be creative. And then you think, how am I going to kind of overcome this impossibility result? So in a similar way, as we kind of relax the notion of soundness to get these snarks, when we relax soundness to computational soundness, they relax the notion of a proof. Okay, so how did they relax the notion of a proof? So just to put things in perspective, proofs have been studied by mathematicians for thousands of years. In ancient Greek, people studied mathematics, proofs. Euclid studied proofs. And despite thousands of years of proof studying, there's a branch in mathematics called proof theory. Despite all these years of studying proofs were always kind of verified line by line. So there was like a deduction. You start with this implies this implies that. At the end, QED, you proved. That's what proofs are. This changed in the mid-'80s with the goal of getting zero-knowledge proofs, this weird thing. How did it change? They considered what's called an interactive proof. So now there's a prover and a verifier, and it's a conversation. The prover says something, the verifier asks a question, the prover gives an answer, the verifier sends a question, and so on and so forth. Moreover, interestingly, the verifier is allowed to toss coins, toss random coins, and the soundness guarantee is different from standard soundness guarantee, which says if the proof verifies, the theorem is correct. That's what proofs are. Here, the guarantee is if the statement is false, you still may accept the proof, but with very small probability. So even if the statement is false, even if X is a false statement, for every cheating prover, P star, when he interacts with the verifier, I have a clicker. When he interacts with the verifier may accept, output 1 mean accept, but with very small probability. Now, you may think that my 0.01 here is not small. It's pretty arbitrary. The point is you can repeat and make this probability as small as you want. Okay? So, but there is a small probability that you'll still accept the false statement, but you can make this probability smaller than, you can repeat it, 500 times, make it smaller than 2 to the minus 500, which is smaller than the number of molecules in the universe. So practically, it's 0. Okay, so for practical purposes, you'll never accept a false statement. But there is this minuscule probability that you will. What a weird way to think of proofs. And now, forget about zero knowledge. This is a revolution. We never thought of proofs this way. Maybe it's more powerful to think of these proof systems. And indeed, so actually before powerful, let me just say, this was a success story. They were able to show that any proof can be converted into zero-knowledge interactive proofs. So this model really served them well for the sake of zero knowledge. But this talk is not about zero knowledge, actually. It's about succinct proofs. And what was noticed soon after kind of this notion was introduced is that interactive proofs actually can be made much shorter and much easier to verify. Okay, so using interaction, you can make proofs much, much shorter. So all these long, long, long proofs can be made much shorter. And let me give you an example. Take chess. Okay, so suppose we have here a chess configuration. And suppose I want to prove to you that the black player has a winning strategy. Which means that no matter what the white player, no matter which move the white player makes, the black player has a move, such that no matter which move the black player is, no matter what the white player does, the black player can always win. That's what it means to have a winning strategy. How can I prove this to you? I mean, with classical proof, proof that you verify line by line, the only way I can think of doing this is actually telling you, listing all the possible ways the white player can move and tell you what the black player will do. And then for every possible move of the white, tell you what the black player will do. And at the end, I'll show you, it's, the black player always wins. This is a huge exponential size kind of proof. So forget it. You'll never verify it. It's too big. I can't even write it down. It's so big. Turns out, with an interactive proof, I can prove it to you much more efficiently, much more succinctly. Why? So I'm going to touch more about why in a minute, but just for intuition a little bit, think of, here's why. I can tell you, you know what? Bring me your best grandmaster. I'll play it. I'll play the master as the black player, and I'll show you that I win. Okay, so I'll just play. It's an interactive process. I'll play, I win. Now, unfortunately, this only proves to you that I can win your grandmaster. It doesn't tell you that I can win any white player, but it kind of shows you the power, if you will, of interactive proofs. Indeed, to prove to you using an interactive proof that I can win any white player is much more complicated. So I'm not going to show you that today. Okay. But, so great. So now we're saying, okay, this is fantastic. Turns out there are many computations that classically will require very long proofs, but using interaction, we can make it very, very short. So that's great. However, by the way, this is a very beautiful celebrated result of Shamir, who was with me, my advisor, remember, that I tried to contradict in the panel? Okay, so, but there was one drawback to this line of work. And the drawback was that while it's very easy to verify, it's very hard to prove. So the prover now needed to work much, much more to convince the verifier. And in particular, a computation that takes, let's say, time t to compute. Let's say I want to prove to you that I ran a computation that takes time t. You don't want to run in time t. T is too much. But I'm going to prove to you I ran the computation, it takes time t, and the output is 1. I can do that with an interactive proof. But now to prove it to you, I need to run in time like 2 to the t. So whereas proving, I needed to run in time, computing, I needed to run in time t. Proving, I needed to run time 2 to the t. Huge. There's no way I can do that. So while this, theoretically speaking, it's beautiful, practically speaking, you can't really use this. So it was like a mathematical curiosity, really. Okay. So then we thought, how about considering like an interactive proof where also the prover needs to be efficient? And let me just mention, prior, people didn't care. It's not like they, even moreover, in one of the works on interactive proofs, they called the prover Merlin, like a wizard. They thought of the prover as all-powerful. Nobody really cared so much about the runtime of the prover. And so we said, let's try to construct what we called doubly efficient interactive proofs, where the prover, the verifier, it should be very easy to verify. Okay, so it should be very short and very easy to verify. But also the prover is not all powerful. Okay, also the prover should not have too much overhead. So if computing takes time t, proving should take time not much more than t. And we managed to prove that there are indeed many computations that can be proven using a doubly efficient interactive proof. Okay, so now you may actually be a little disappointed because what I delivered is not what I promised. I promised succinct certificate, and I'm giving you interactive proofs. So where's the certificate? It's an interactive thing. Remember, I promised a SNARG, a succinct non-interactive argument, and I'm giving you interactive. Secondly, I promised you that I can convert any proof to a succinct one. And now I'm telling you, oh, not some computations. There's some computations, many, but not all, many, that I can make succinct using interaction. So this is not what I promised. But so far, I didn't use my magic wand, and I didn't sprinkle cryptography in it. So turns out that when I can use cryptography two ways. First, I can use cryptography to eliminate interaction from the interactive proof. So I'll first give you an interactive proof, and then I'll use cryptography to kind of reduce all this interaction. That's one place where I'm going to use cryptography. Another place is I can actually not just do for many computations, I can actually use cryptography to convert any proof into a succinct interactive proof, and then go to the one above, to up here, and eliminate interaction. Okay, and by the way, the eliminating interaction is by a beautiful paradigm, again, Shamir, my advisor, by Fiat and Shamir, and I'll talk about it in a minute. Okay, so the second point here, I'm not going to talk about today, so bye. I'm only going to talk about the first point. And I want to point out one thing about this approach that's pretty remarkable. I want to construct succinct proofs. What is my approach? These succinct certificates. What is my approach? I'm going to first construct interactive proofs, and then I'm going to eliminate interaction using cryptography. Kind of seems like a bit roundabout way, but that's actually how we construct these succinct proofs. Okay, so let me spend a few minutes just telling you, okay, how we actually do it is complicated, but I want to give you a little bit of intuition how this is done. And for the sake of intuition, I'm going to show you an interactive proof for some computations. Because it gives, I think, the intuition. Which computations? Those that are kind of a low-depth circuit. So here you have a circuit. Each gate here, you can think of it like a addition or and or whatever. You can think of it like and or and not gates, if you want. And I have here a computation. Okay, so you have this is the input. And let's say I want to prove to you that when you compute the circuit on input x, you get 1. Okay? And think of this as a very shallow circuit, but very wide circuit. No, it doesn't quite look like that in the picture. But think of it as wide and shallow. Okay. I want to prove to you that the answer is 1. How do I do that? So here's the idea. I'm telling you the answer is 1. You're like, I don't believe you. So I'm going to tell you, okay, here, let me prove it to you. I'll give you the 2 children. Check that the gate is satisfied. Now, if I cheated, one of the children is not true. The value in one of the children is not true. If one is not true, one of the children is not true. So you guess which one. Let's say you think the left one is not true. Now you tell me, show me the 2 children. If the left child was not true, one of the 2 children is not true. Guess which one. And so on and so forth, until we reach the leaf. Now, if every time you guessed correctly which one was not true, you'll arrive to a false leaf. So you won't get x3, and then you'll catch me. So this is an interactive proof. Every time you guess which one, It's low depth, so it's very easy, and then you'll catch me. Okay, that's not satisfying because it's another one of your guesses was wrong, and you failed. So to catch me each and every time your guess of where the false child is needs to be correct. And that happens with very small probability. So it's not good. This proof is pretty pathetic. And the way we improve it is essentially by, instead of going over the circuit itself, always choosing left or right, we do it over kind of an error-correcting code. So what is an error-correcting code? An error-correcting code, the idea is that if there's one value, if one of the children is wrong, the entire layer, most of the layer is wrong. So we kind of extend the layer using what's called an error-correcting code. I'm not going to say anything about it, just say that it exists. There's a way to encode each layer of the circuit so that if one of the children is wrong, almost all the extended layer is wrong. And then we do the kind of the same idea over kind of the error-correcting code. We, again, reduce kind of from layer to layer to layer. How we do that? Complicated. It involves some algebra. It's not too complicated, but it involves some quite heavy algebraic techniques that I won't have time to talk about today. Okay, so I don't want to say too much more about that. The point is just to give you an idea of how interaction is useful. And in the last couple minutes I want to say a few words about this Fiat-Shamir paradigm for reducing interaction. And this Fiat-Shamir paradigm, or heuristic, is extremely popular. It's used all over the place. And the idea is it takes an interactive protocol and eliminates the interaction. And how does it? In a very beautiful and simple way. So suppose, for example, you have only 3 messages, a protocol. You can do it for many messages, but for many rounds, but let's say you have 3. Okay, alpha, beta, and gamma. And suppose it works only if the protocol is what we call public coin. Public coin means that the messages from the verifier are random. Okay? Let me just mention our succinct interactive proof are public coin. The messages from the verifier to the prover are just random. That's important. And now, how do they reduce interaction? They tell the prover, you choose alpha like you would do here, and you also choose beta. You compute beta on behalf of the verifier, and then give the answer. Now, that won't work, because if he gets to choose the verifier's message, he can cheat. So we tie his hands, and we tell him, OK, you get to choose beta. You get to compute beta. But beta, you don't get freedom. Beta, the message from the verifier, is some function h of your previous message. So you choose alpha. You don't interact with the verifier. There's no verifier. But you compute on your own the verifier's message beta to be some function h of alpha. And then you choose gamma, like you would here. And now, if you use, now the question, so that's it. And the idea is, which h do we use? Which function h? Use something that looks really random. That's the idea. How you choose h is a very good question. But that's the idea. And now the question, is it secure? Well, it depends which h you use. For which h is it secure? OK, so let me tell you, in practice, this is used everywhere in practice, and it works. There was never an attack in practice. But is it really secure? We don't know. And let me tell you, this is a bit of a worry, because every person here who uses an iPhone or an Android, I assume it's probably all of you, you rely on the security of this paradigm because you use digital signatures that rely on the security of this paradigm. So it's your own benefit to hope that this paradigm is secure. Now, is it secure? We don't know. However, let me tell you something a little worrisome. OK, we don't have attacks, but can we prove that it's secure? Like, can we prove that that there always exists some function that if you use it, in the Fiat-Shamir paradigm, you would get something that's secure? And the answer is no, actually. We actually have examples where you start with something, a protocol that's sound, it's good, like some protocol. No matter which hash function you use, it's not secure. So that's a bit worrisome. but it's a really contrived example. So don't worry, you can sleep well at night, okay? It's a contrived example. But my point is we still don't understand fully this paradigm that we use every day, all the time. But what we did manage to prove is that our doubly efficient interactive proofs are sound. That specific proof that we managed to construct in the interactive setting, if you apply Fiat-Shamir to that, then it is sound, under some standard cryptographic assumptions that I don't want to go into. Okay, so I'm kind of out of time, so let me just wrap up and say that this entire journey was really fun, and it was, as a community, I think it was a really success story for the theory of cryptography. It started by just a bunch of theorists working together, and then this thing was kind of, these things were moved from theory to practice. A lot of people, more applied researchers, started prototyping it. And as I mentioned, by now it's used, it's deployed. And moreover, now we have like a big effort together with theorists and applied people and product and people from the industry trying to standardize it. It's an effort called ZK proofs. Because often we put zero knowledge on top that I didn't talk about, but now it's in the process of standardizing it. So it's really kind of a fun collaboration all around. And I want to end by, again, putting up my amazing collaborators and thanking them for taking this journey, this really fun journey with me, and to thank you guys for your great attention. Thank you.
Thank you so much, Professor Kalai. And now, may I take the honor to invite Dr. Sun on stage to moderate the Q&A. And later on, during the Q&A, could I invite participants to introduce your name and your institution before asking your question? Thank you so much.
Thank you.
Hi.
Hi.
Thank you very much for the very enlightening lecture. And amazingly, without any mathematics, without any equations, you are showing ideas and also showing the impacts of going through the mathematical journey and then come to the deployment. So with this, I would like to invite our audience to come to the mic at the two sides of the corridor to shoot your questions. Great.
Hi, my name is Gary. I'm from A-Star. Thank you so much for sharing. It's really spectacular to see some of these mathematical treatments and approaches. My question might be a little more general, taking this a bit broader. So from the context of AI, and I think there's also some efforts in doing verification proofs with AI methods. One of the things I realized in my discussion with my colleagues is that for these AI methods to actually be able to use some of the tools that have been developed, or at least in some other methods, there is a need for certification or some particular ways that the method has to adopt in order for you to be able to unlock some of these tools for proving, for verifying. But it seems like that could be really tying some of the AI methods, constraining them, tying hands behind the back, and might actually cause performance degradation. And that might be why there isn't really a motivation towards that space. So my question to you might be kind of twofold. One is whether there is a way of tackling this, and what would be a good way of really motivating for us to enter this space of really looking into proof verification with AI methods without the fear of just pursuing better performance.
Yeah, so, succinct proofs in the context of AI. There's two things that one can talk about. One is how to use these succinct proofs. I'm not sure which one you're interested in, but let me say both. One is, can we use our technology of succinct proofs in the context of AI? For example, won't it be great if we can ask the AI to give us a succinct proof that it's not hallucinating and it's given us the correct answer? That's one question. And the other question, and I have a lot to say about this, it's actually a very active area of research that we're thinking about. The other question is whether we can use AI tools to just construct these, to take any proof and make it shorter. And for the latter, I I mean, I'm not sure we need to use AI tools to do that because we know how to do it without AI. It's pretty efficient in practice, and it works. And I'm not, you know, we know it's a problem that we solved. We need AI to solve problems we haven't solved yet, and this is something that we have solved, so we're in a pretty good way by now, so that works. Regarding the first point of trying to use these succinct proofs in AI, it's much more complicated. And the reason is, we don't know what it's doing. You know, I can certify correctness of a computation, but I don't, if you tell AI, run this here's a program, run the program and give me a proof, that he can do for you. But that's usually not what we use AI for. If we had a program, we'll run it ourselves. Usually, we don't know what we want the AI. We don't know what computation. We're hoping it will know what computation to run for us. We just ask a question. And so we don't even know what it's doing. So what does it mean even to ask a proof of what? That it's doing what it's supposed to? What is it supposed to do? So these kind of questions are questions that we think about a lot now. That's kind of our new kid in the block that we're trying to tackle. But I still don't have, maybe next year, I'll come with answers.
Would love to, looking forward to hearing more about that in the future. Thank you.
Thank you.
Thank you. So we turn to the left-hand side of me. Yep.
Hi again, Lisa, University of Tampere. I have a question about interactive proof and then generating a certificate. So from what you said, and I understand, with interactive proof, we assume there might be some probability of it's wrong, and until, how wrong it should be, so we cannot generate certificates. So what's its percentage? So shall it be 5%, 2%?
Yeah. So actually, typically, the probability of being incorrect, you can think of as 0. Because the way we set the parameters is that it's going to be incorrect with probability. Usually people use 2 to the minus 100. 2 to the minus 100 is so small that, there's a much bigger probability that I'll get killed when I leave here in a car accident. So, I mean, it's much, much smaller than that. You can really, and if you're not happy with 2 to the minus 100, you can make it 2 to the minus 500 by paying a factor of 5. And then this probability becomes smaller than the number of molecules in the universe. So there is a probability of error, but practically speaking, there is no probability of error. It's so small that practically speaking, we should think about it as 0.
So it should be some concept which is we almost sure it's always right.
Yes,
Okay.
exactly. You should think of it as always right. That's the right way to think about it.
Okay, thank you.
Thank you. So we turn to the right-hand side of me.
Hello, my name is Daniel. I'm not an AI expert, but I do want to ask whether this technique can be used to verify whether an output is generated by a given algorithm, for example, to detect AI-generated content. If we say know that a GPT model is being used, can we use this to know whether it's highly likely that a given set of outputs is from this model or not?
Okay, so with AI, the situation is much more delicate. Let me tell you what we do know. If you tell the AI, compute this, here's a program, it runs too long, I can't run it on my own, I want you to run this program for me, generate the output and give me a proof, it can do that for you. AI will be able to do that for you, okay? If you ask the AI a question that you don't know the answer for example, when will climate change make this place, this city in the world inhabitable? We don't really know the answer. We ask AI, and it will tell you, 50 years. Now you ask him, give me a proof. A proof of what is the question? It can prove to you that it ran its algorithm, so an AI is some circuit, some algorithm, and it can prove to you that it ran its neural net or whatever it is that it has, and that was the answer that it got. That he can prove to you. But what does that mean? It doesn't mean that indeed that his algorithm is true. It means that he ran its algorithm that was trained on whatever, and that's the result you got. So that it can do for you, but what's the meaning of that?
I guess it's whether, can we use it to distinguish between human-generated content and AI-generated content?
Oh, can we use it to distinguish between human-generated and AI-generated?
Sorry.
that, I'm not sure it's super well defined. Like, you can, okay, he can prove to you that he generated it. That it can do. It can tell you, you can ask maybe OpenAI to send like a succinct, what we call succinct commitment. We have this notion of a commitment to their algorithm, like a succinct thing, and like some certificate, and it can prove to you that it ran the algorithm that was committed to, and that's the answer it got. So it can prove to you that it generated, that it ran its own kind of neural net. But beyond that, I'm not sure even what else can we ask for. You see what I mean? There's a lot of philosophical questions about what is it that we want it to prove. I think if we understand better, if we have a good understanding of what it is we want, we can get it, is my guess. But actually, asking the question in a way that makes sense is very hard. That's kind of where we're stuck now. And we have some partial results, but the big question is still there.
Thank you.
Hello, my name is Bahar. You mentioned that nobody knows what happens inside, like a neural network, that kind of like the big ones that gives us answers. Can you reflect on that? Because I cannot wrap my head around, like, if you are making an algorithm and you know what happens in the algorithm. So why can't you know what happens when you are actually deploying it?
Yeah, so, okay, good. So, when we train a neural net, we give it data, and it generates these weights, and so on, and comes this circuit. Now, what is the circuit doing? Why are these the correct weights? Is the output that it produces now, are they good or are they not good? We don't really know. We don't know, we don't know why. Why are they so successful? In the beginning when people started, I remember there was a time when all of a sudden all the talks were, okay, we trained this neural net and we got amazing results. Why? Well, we trained, it worked. And they give you evidence, like you see, they give you data and it works on the data. But why does it work? I think we still don't quite understand. So when you train our LLMs, which is a huge, much more than just a small neural net, it gives you a result. You don't actually know if it's correct or not. We don't know. It gives you a result. It tells you something. Does it hallucinate? Does it not hallucinate? What is it that it's doing? We currently, that's what we talk about the panel about inexplainability. We have no idea what's going on. We trained it. We gave it tons of data. We ran it, and out came a circuit. Why is this a circuit? What does it do? Is it a good circuit? We don't have answers to this question.
Do we know why we don't know?
That's a great question. That's a great question.
Yeah, that was my actual original question.
Good. Good. So actually, we talked about it in the panel a little bit that some people said, oh, it's a lost cause. Like, we can't. There's no hope for explainability. Why? Okay, prove to me that you can't explain. Do we know? No, there's no proof that you can't explain. So we don't know why we don't know. I mean, people are still trying to figure it out. People are working on it. But we're still in the dark. So we don't know.
Thank you.
Right. I think, we are turning to the last question for this session.
Hello, thank you for your extremely unique topic of presentation. My name is Anna from Seoul National University. I have a very general question, actually. I'm just curious, how does one get into this line of research, cryptography and proofs, and what exactly sparked this curiosity for you? And then the second one, does it involve collaboration with researchers from other fields?
From other fields, good. So for me, what sparked me to get into this topic? So actually, I started my master's degree in Israel. It goes first undergrad, master's, and PhD in the Weizmann Institute. And I had no idea what I'm going to do. I was interested in math, so I thought I'll do something theory, but which theory to do, I had no idea. And the truth is, for me, I remember taking a class with Adi Shamir, and I was so blown away and I remember thinking, okay, I really want him to be my advisor. And I remember a friend of mine told me, how do you know is his main research area cryptography? Maybe he's just teaching crypto. You don't necessarily teach what you do. And I remember saying, I don't care. I'll do whatever he does. Like, I want. He was just inspiring. I was like, oh, it's not crypto, so I'll do whatever. I'll ask him what he does, and I'll do that. So I was inspired by his personality. And then but I'm sure if the field wasn't for me, I would leave. So it's beyond that. And how did I get into, I really enjoy things that are, I like math, but I enjoy the philosophical thing around it. Like, how do we define knowledge? How do we define, things that are a bit more philosophical? And I also enjoy things that have impact. While I like math, I'm in the computer science department, but I don't code. I don't actually know how to program. Embarrassingly enough, my kids are shocked that I'm still, they haven't fired me yet, even though I don't know how to program. So I wanted something mathematical, but when you do math, like pure math is often incremental. It's very hard to make big impact. And in cryptography or theoretical computer science, it's an area it's still very mathematical, but it's much easier to have an impact. And like the Fiat-Shamir paradigm is an example where it's had a huge impact, and it's very beautiful, it's elegant, it's simple, but we don't understand why it works. This is a problem that I've been working on from, he was my advisor. I had to prove that I actually wanted to prove that it's secure. I was like, I'm going to impress him. I'm going to prove that it's secure. And I worked it for a very long time. And I remember my father telling me after a while, because I was frustrated, he's like, maybe look for a counterexample then. And I'm like, no, I'm sure it's secure. He's like, well, if you didn't prove it, maybe there's a counter. And then we found a counterexample. So I think I really enjoy kind of problems that are interesting, like have impact, but yet mathematical. So that's kind of what drove me to this field.
Thank you so much. Wonderful.
Thank you, guys.
Wow. We are coming to the end of this session. Some of the questions have been asked on my behalf, especially I think toward the last part of the session. When we have the difficulties, challenges, and also how do we persist and then coming to the final stage and then making impacts. How do we make choices for challenging and yet potentially impactful research problems for us to go forward? I believe this session has given us many enlightening examples and also open up some of the research problems for our young generations of the researchers to go and pursue. And with that, I'm coming here to ask you and join me thanking Professor Yael Kalai for the very enlightening lecture session.
Thank you.